Pop quiz. What's the one thing that stitches every talk today? Stitches together every talk. You could not have had each one of those talks without one thing and only one thing. What is it? Energy. Energy. Everything you saw here started with energy. Everything in this room started with energy. You all know it. It's in front of you, and we can't even imagine it. Think about that. You take it for granted. So, second question. Under the umbrella of energy, it's everywhere, and it's fundamental to modern life. So this morning when you flipped the lights on, I bet you weren't like going up on DraftKings and figuring out whether it's going to come on or not, right? You were pretty sure they were going to come on. When you charged your phone and you were hoping for it to go from red to green, I don't know about you guys, but when I'm below 50%, I'm looking for a charger, okay? I have range anxiety on everything. The elevators. Look at all this stuff that's going on in these pictures behind me that we all take for granted. So let me just describe energy for you a little bit, because in the spirit of Sesame Street, we're going to have two words today that we're going to keep coming back to. Technology and scale, because that's what underpins energy. You got to have technology, you got to have science, and you have to have scale. So let's talk about technology. You know, if you want to be a chemist, what do? You study chemistry. If you want to be a pharmacist, what do? You study pharmacy. You want to be a broadcaster, you study broadcasting. What do you want to do if you want to be in energy? You have to study everything. It requires every discipline of science, math, physics, chemistry, biology, and every discipline of engineering, chemical, mechanical, nuclear, civil, electrical, every discipline, all integrated together. That's technology at scale. It's just a different type of scale. It's integrating it all together. How do all the pieces fit? Now let's talk about scale, because units are really hard to understand. We talk about millions of barrels a day, 100 million barrels a day. We talk about gigawatts and terawatts of power, and most of you don't even know what that means. But if I asked you what a gigawatt is, you would know what a gigawatt is, because that's how you get a DeLorean to go from 1985 back to the 1950s, and a gigawatt's not even a thing. So the scale of this, millions of barrels a day, exajoules of energy, terawatts of power, is huge. It's everywhere. It's fundamental to modern life. And yet, there's 1 billion people out there that don't know what I'm talking about, that don't have access to affordable, reliable energy, that quite frankly just want to live the life we've been living. And you've heard that from the various talks today. How do we improve quality of life? Well, the first thing you do is you provide energy. It changes the way you cook. It changes the way you go to school. It changes the fact that you can go to school. It changes your water. It changes your medicine. It changes everything. And for the longest time, we didn't know if we'd have enough energy to even get to the point where we could have access to energy. And again, because of technology, and because of technology at scale, we can see line of sight to that now. Why is that? Well, in the US, for instance, right, we developed a thing called fracking, which allows more oil and gas. We learned how to ship gas around by turning it into a liquid called LNG. We brought in solar. We brought in nuclear. We brought in all forms of energy. The number of forms of energy we have today, relative to when I started several decades ago, is quite frankly mind-boggling. So we have line of sight to this. How do we get that 1 billion people today? And remember, this doesn't stop, because there's 2 billion more coming, largely in the developing regions. So this is a scale challenge that continues to build upon itself. And we've got to figure out how to do that. So you think, okay, well, he just said that we know how to do that. But as often things turn, you solve one problem and you have another challenge. And the challenges keep adding in this space. And so we're going to talk about the challenge we're all facing today, which is how do we do more and reduce emissions? And guess what, guys? That's another technology at scale problem, okay? How do we do this? How do we provide the energy while reducing emissions? Well, For those of you that are kind of mathematical, you look at that and say, well, that's a two-variable equation, Vijay. Two variables. This is not a problem. Two equations? Come on. Well, it's not two equations. Think about energy. Think about the fact that it has to serve different sectors. The way power is addressed is going to be different than transportation. Transportation is going to be different than heavy industry. And then you have subsectors. The way you move a car, yeah, you can do that electrically. I don't think you're going to do that to an airplane. Thermodynamics really does matter. And you need a liquid hydrocarbon fuel to move an airplane. So you go from a two-part equation, challenge, to now you have multiple sectors. And let me add one more thing. You can have geographic differences. So the solution for China is going to be different than the solution for Germany. It's going to be different solution for India. It's going to be different for the solution in the US. And within the US, we have 7 grids. So you're going to have sub-solutions in the US. And you know what? Some of you guys are thinking, he's describing a Fibonacci sequence. This is incredibly complicated. It's complex. But the problem is simple. We want scalable energy, and we want to reduce emissions. That's the challenge. And we're going to talk about that, and I'm going to try to put it in context, and then come back and talk about, well, what are we doing? How do we actually do this? Because it's a problem that covers time scales, covers magnitude, covers spatial scales, all of those. It's a challenge of a lifetime. And I'm really excited that there's students out there. I'm going to come to you near the end of the talk. But this is a generational challenge that we're on. And we've got to get at it. So let's talk about that. And I'm going to come back to the 2 words of today, scale and technology. We're going to need it to meet the demand for energy. And we know how to do this. And Ponch started by talking about inventions that the National Science Foundation works. And we work with the Department of Energy, we work with the national labs, we work with the universities, we work with everyone, but you got to have line of sight to scale. And what I'd add to Ponch's discussion is the magic of energy is going from invention to scale. And the bridge between invention and scale is innovation. And if you think about the numbers of innovations as you look at these pictures, just think about all of this that has to happen at the scales we're talking about. For your lights to come on, for your cars to move, for the airplanes to move, everything here. We know how to do it. We've done it. We've collaborated. Think about the things we've done, from fracking to lithium-ion batteries to solar panels, much of which has been developed in the US, invented in the US. All of it which has been scaled by industry. That collaboration, that way we move science and technology from concept to scale, is what we need to focus on. And again, we know how to do this. We now have a new set of challenges, which is we've got to continue to do this, providing the energy, reducing the emissions. Now, as we're doing that, I know you know this, and we've talked about this already a couple of times today, about it has to be continuous. There can be no gap. You want your energy, you want it to be continuous. You don't want intermittency, you don't want the lights to come on and off, you don't want the fuel to not necessarily work. This isn't digital where you can, send out a patch and you can fix something, right? This is full-blown. You want industry to operate, you want transportation to work, you want power to work. And therefore, as we're navigating this transition, not a switch, a transition, we have to remember the key conjunction. So we didn't get into Schoolhouse Rock. We talked about Sesame Street. We talked about CNBC. Remember conjunction junction on Schoolhouse Rock? The word is and. The word is and. It's not or, it's and. And so we have to do that. We have to first recognize that the current technology is insufficient. So how do we do this? As this screen rolls behind me, take a look. The International Energy Agency just looked at the 55 needed technologies, and you can see it's broken out by subsector. So you can see for each one of the sectors, I talked about the subsectors, and you have simple traffic lights, red, yellow, green, that tell you whether you're on track or not. And you got to look hard to find the green, because 53 of these 55 are not on track. Now let's start with the good news. We know what the 55 are. That's good. We know what the 55 are. We know we've got to get the current technology to go at them. And if you looked at the industry in particular, right, this is really hard. This is steel, this is iron, this is cement, this is refining, this is chemicals. People often forget that energy itself is energy intensive. So how do you turn these lights from red to yellow to ultimately to green? It's recognizing that what you have right now needs more work. That's okay, we need more work. We have to continue to provide energy. We have to look for ways to reduce emissions. And I should add that efficiency is one of the knobs to turn. So the more efficient you get, the better off you are with the energy. So if the current technology is insufficient to meet the global demand, which is a fact, but we want energy and we want to reduce emissions, we come back to and. We come back to we have to do the and. And so what do I mean by the and? What I mean by the and is we got to deliver today and position for tomorrow. That's the whole point of a transition. You want to go as fast as you can, as hard as you can, and when the technologies are ready, you need to deploy them. So what does that mean? Well, we need to continue to provide more energy today. And you're seeing it in the US. You're seeing increased oil and gas production. You're seeing increased chemicals production. You're seeing refineries expanding. We just expanded a refinery. And just to give you some units, we expanded a refinery by 250,000 barrels a day. When I started it back in the dark ages, that was a world-scale refinery in itself. And now it's an expansion. The scale of this industry is amazing. So we need to deliver today. And as Tyler said, we need to be researching and developing and deploying the technologies for tomorrow. And what do those include? Well, those include carbon capture, as he mentioned. Take the CO2 and don't let it get into the atmosphere. Catch it from the point where it's emitted, or pull it straight out of the air. Take it, sequester it safely. That's a good thing to do. Switch to fuels to biofuels. So as the fuel is being grown, if you will, CO2 is being pulled out of the air, such that when you combust it, you're more or less in balance. That's a good thing to do. Hydrogen, you hear a lot about hydrogen. Why do you hear about hydrogen? When you burn hydrogen, there's no CO2. It's water. The question is, how do you make the hydrogen? You can make the hydrogen from a CH4, which is methane. You can make the hydrogen from water. Split water, take H2O, you can make water from biomass. So there's different ways to do it. The good news is we need lots of shots on goal to get to the scale. And remember, geography is going to matter. Policy is going to matter. Technology is really going to matter. And the technology at scale is going to be absolutely vital. So we've done this. This industry has been around a long time. It's always been rooted in science and technology. It's always been about meeting demands of society, improving quality of life. That is what we do. And we have to keep doing that while we're positioning for tomorrow. That's the what. Now let's talk a little bit about the how. Collaboration. And that's actually, while imagine is one of the themes, the other theme you're hearing about is collaboration. When I talk about collaboration for energy, I'm going to talk about it in 4 dimensions. I'm going to talk about it in universities, governments, smaller companies, and large companies. They need to work together. And let's talk about the roles real quick. Universities. When you heard Ponch speak this morning, he talked about the funding, and a lot of the funding goes to universities. Why? Because that's where fundamentals happen. And the nice thing about universities is graduate students, and I was one of those many, many years ago, they're kind of it's a continuous flow. So you have constancy of purpose in the university to continue to push the envelopes and further understand, further understand, further understand. That's great. Governments with their national labs and national research foundations and national science foundations and all those types of things can really help because they have the breadth to have a wide array of analytical equipment, a wide array of other types of equipment that no one company or no one university can have. So it's kind of like a public library. You can use the equipment, you can use their testing facilities to try out ideas. That's really important. Smaller companies, what's their role? First, deployment. Getting on a deployment curve. Because what you want, the way you have to do 2 things simultaneously. You have to scale up and you have to bring costs down. Scale up, cost down. First, deployment. How you get on a deployment curve, how you come down a cost curve as you go up a scale curve is critically important. And then finally, you've got to get to that scale. Large companies like ours that have the project expertise, the capabilities to do projects. Now, I'm going to challenge what I just said, because what I just described was a series approach. And one of the first things you learn in physics is parallel processing beats series processing every day. So if we want to accelerate, we have to collaborate. And I can't play the piano. That's as close to a rhyme as I can get, okay? If you want to accelerate, you have to collaborate. And then the other thing you have to do is you've really got to do things in parallel. So while the fundamentals are going on, are you answering a question that's going to help us scale? If you are, that's a pretty important question to get, because you might be able to tweak what you're doing in the lab with line of sight to scale. That could be choosing a different metal, because the metal you're using, there's like 5 drops of it or 5 grams of it in the world. You want to use something that's plentiful. You want a large raw material. As you're getting to the first deployment, you're asking yourself, how is this going to scale? What should the first deployment size be? And how can I go from n equals 1 to n equals n? How can I get to that nth deployment so we can get the cost down and the scale up? That type of collaboration is going to be critical. Now, like I said, we've done this before. And what's underpinned energy for hundreds of years is the power of science and innovation to go from this picture to the next, which is where we want to go. And that's where the students, I'm guessing you got a day off. This is a field trip. You got out of school today, which is fantastic. And you're getting to see all this good stuff, because it's really critical that we inspire and motivate students, that we help them imagine a world where we do have the energy we want, and we've managed the emissions. And we've done it because of the technology, because we've unleashed it. And yes, technology, science has to work with policymakers. Technology, policy, infrastructure all have to come together. We've got to come together working in the same direction. The previous speaker talked about how do we bring everybody together. This is one we're all in agreement. We all want to provide energy. We all want to reduce emissions. How do we go about doing that? Well, the common barrier, the common ground here is science and innovation. We've got to continue to drive technology. We've got to continue to encourage the next generation of leaders to take up math and science and chemistry and physics, to go to university, study these things, and then pick your position on that chain I talked about. Universities, national labs, small companies, large companies, everything's needed. It's all of the above. It's all good. We're sitting in an Imagine conference. I will tell you, if somebody had given me a blank sheet of paper 35 years ago and said, describe energy in 2023, I would have not done very well. I would have not imagined what we're able to do today. But with the power of science and the power of technology and the power of innovation, I'm absolutely convinced that we can address this and we can continue to provide energy while reducing our emissions. Now imagine that. Thank you very much for your time.